Hello everyone, I'm Marc and I'm going to talk to you about key differences between Cairo and EVM execution. This talk is mainly focused for developers that already develop on Solidity and are interested in exploring building on StarkNet using Cairo. So I work at ChainSecurity. I'm doing smart contract audits actually. We are working with many big players in the space, and we sometimes have to audit also like Cairo smart contracts. So that's where actually most our knowledge will be from today. Okay, about me, as I said, I'm doing the audits. I audited like Euler, Velodrome, Polymarket, worked on many more the project. I initially come from a more like traditional background, doing CTFs, and I previously worked on baseband. First of all, here are some like nice resources that I would recommend to everyone to explore, to have a look, because those are your main go-tos if you want to start building actually on Cairo. So there's a Cairo language book, the StarkNet book, of course, to understand what chain you're building on, how like all the properties of that chain, and then of course the StarkNet Foundry book, which is the environment you can use to actually write smart contracts. So let's get started. What's the main differences between Solidity and Cairo on the high level? So Solidity is this object-oriented, statically typed C++ style language. So it's very close to a traditional programming language, but really focused towards smart contracts. On the other side, Cairo can be also used for general computing, but its main benefit is that it's designed for verifiable computing, which means from a program you can generate a proof very easily, a Stark proof actually. Cairo is a Rust style language, so it will also inherit from a lot of the properties that Rust has. For the memory model, so Solidity, I guess you must be familiar with it. Each slot in memory is bytes 32. The memory is mutable, completely, there's like free access, right? You can do what you want. You can write a contract and have some UL assembly changing the free memory pointer. You can do whatever, right? Like no one will tell you you cannot overwrite this part of memory. For Cairo, it's a bit different. So each slot is a felt 252, which is 252 bytes large, and a felt is actually the basic data type in Cairo, which stands for a field element, which is actually the underlying type used to highly optimize Cairo's ZK-proof system. And something interesting is that the memory is completely immutable for Cairo, which means you cannot overwrite a memory slot once you have written to it. However, on the language level, mutability is implemented through shadowing, so you can use the mute keyword, and the compiler will handle it for you and let you reuse the same variable, but under the hood it will allocate a new memory slot. There's also something called snapshots, which is an immutable view of the memory at a certain point in time. And Cairo memory also has the ownership concept as Rust. Having immutable memory leads to less flexibility, but also less chance to actually mess up memory. And for example, arrays in Cairo are actually just queues, because you can only remove elements from the front and append new elements to the tail, as this only involves pointer updates and not, memory updates, as you cannot overwrite a slot. For the storage layout in Solidity, so as we know, the order in which we declare our storage variables will influence which slot those variables are assigned to. So from 0, incrementing by 1. We know that for dynamic arrays, the array will start at the Ketchak 256 of the slot. For mappings, each value will be at the Ketchak 256 of the padded key appended to the slot of the mapping. There's no size limitation of single objects, and there is, by default, storage variable packing. For people who don't know what storage variable packing is if a type is smaller than a byte 32, it can be possible that multiple such storage values are actually written in the same slot. Shadowing storage variable does not compile actually. So if you have a contract B and a contract A that extends B, if they declare the same storage variable using the same name, it won't compile. On the other side, Cairo has in storage just two types, so non-mappings and mappings. Non-mappings actually are stored at the SN catch-up of the variable name. So that's something very important to keep in mind here, because the name of the variable influences where your variable will be stored in storage. And the SN catch-up is the lower 250 bits of catch-up 256. And for mappings, it's very similar to the solidity case, just that we also use this variable name instead of the slot. There is no default storage packing in Cairo. However, it's possible for structs that implement the store packing trait. And there is actually a warning if you have shadowing storage variables. So if you have two components that have the same storage variable name, it will give you a warning, but it will still compile. So as we can see here, on the Cairo side, if we have the component A and the contract B embeds A, they both have this same storage value, which will actually point to the same storage slot. So that's something to keep in mind when using libraries, for example, that you might change values that you don't want to change due to the variable name being the same. Now let's discuss a small difference between Solidity and Cairo in terms of operator precedence. In Solidity, the equality operators have less precedence, have less priority than the inequality ones. However, in Cairo, they have the same. So this is not a big issue because usually, because in Cairo, the type checker will catch some bugs due to the fact that booleans are not like integers by default. But if you start to do operator overloading, this might be something that you want to keep in mind due to the operator precedence difference in this case. So let's have a quick look on like transaction cost in terms of, I mean, it's written Solidity Cairo here, but it's mostly like Ethereum and StarkNet, so sorry about that. On Solidity Ethereum, you pay actually for the resources you use, cold data size, opcodes, memory storage accesses, blobs. On Cairo, you have multiple components, right? So you have the DA cold data cost, which is the fee to actually push the state diffs to L1. It is a lower cost if you use blobs, of course, but if you use cold data, it will be more expensive. Then there's the message cold data cost if you want to send a message from L2 to L1, so L2 being StarkNet in this case. There's also the storage write cost, which is the fee for writing on to the Ethereum storage. And since StarkNet 0.13.1, there's also this L2 data cost, which is a per byte cost for cold data events and code. And there is computation cost, of course, which is non-deterministic because it depends on the amount of built-ins used in the same block. I will not go too deep into this because it gets quite intricate, but I recommend you to look up the gas estimating docs. So now something more interesting that you might have heard since a few years, like reentrancies, the big issues in smart contract usually not anymore. I mean, not too much anymore, but still always relevant. In Solidity, view functions actually are usually called by a static call, so you cannot actually do any storage changes, right? You cannot write storage, and if you try, it won't compile. However, there's an equivalent in Cairo for view functions where you pass the self, the contract state, and it will make sure that you don't try to modify the contract state using self. However, you can still do a low-level contract system call that allows you to actually change the contract state. So view functions don't guarantee no direct reentrancy due to the fact that those low-level calls can be performed. Hence, developers should not have the assumptions that calling a view function on another contract cannot modify state. So that's an assumption you have to keep in mind when also integrating with smart contracts on StarkNet. Now a small note about like bridges. So the StarkNet token bridge from L1 to L2. The interface on L1 expects a uint256 array of payload. However, the array must be actually an array of felt 252 represented by uint256 due to the fact that the basic type is different for StarkNet, which is felt 252, only having 252 bits, which means if you actually exceed the felt 252 max value, the message will get stuck in the bridge and you have to cancel it, and I mean, it will lead to some trouble. So you have to keep in mind that the types are not 100% compatible, and you should always make sure that you use the correct serialization scheme defined in the Cairo documentation. Yeah, proxy and clones on StarkNet are actually natively supported. So for example, when you deploy a contract, you would have two steps. First, you would declare the contract, which is registering its class hash on StarkNet. The class hash is computed from the compiled contract bytecode. But when you declare it, it does not deploy a contract. You have to actually do a second step, which is a deploy transaction that actually links the deployed contract, which links the contract address to actually one of the class hashes. And this means that if you want to upgrade a contract, you can simply use the replace class syscall, which would replace the class hash of that specific contract. You have to, of course, implement a function in that contract to call it. Make sure, of course, that the access control is set. And when you upgrade, make sure that the variable names match, right? Because as we saw earlier, the variable names actually influence where they are stored in storage. And of course, when you upgrade, you should always check the compatibility with other contracts you are integrating with. Yeah. Account abstraction is actually also natively supported on StarkNet through the StarkNet Improvable Proposal 6. So you can implement this ISRC6 interface, and what will happen is when a transaction will be executed, the sequencer will actually first call into validate and to verify if the transaction is valid, and then it will call once again validate right before this execution. And there are some caveats here, of course. You should make sure that validate can only be called by address 0, which is the address of the sequencer. And the timestamps and the block numbers are actually rounded. So the timestamp is rounded to the hour and the block number to the lowest multiple of 100. And this is because the validate step should not be too precise, as we don't want the first validation to pass, and the second to fail, which means we are actually using resources for nothing, as the execution will fail. For testing, just a quick side note. So if you plan to develop on Cairo, you can use SN Foundry, which provides a very good testing environment. I mean, I'm sure you all know Foundry that is used to develop Solidity contracts. So there's an equivalent here for Cairo. It supports cheat code, fuzzing, parallel test execution. So that's what I recommend to use also. So here we have some conclusions about what we just discussed, right? So there's a different memory and storage model between Solidity and Cairo. There is slightly different aperture precedence that could lead in the theory to some issues. The most important part here is also that it's possible to have reentrances on view functions in Cairo. And proxies and clones are supported natively, which is also very nice as a developer. Very good testing frameworks, and of course, Cairo is great also for DeFi composability. So, yeah. Thank you very much. This was my first talk. I hope it wasn't too bad. And hi, Mom. Thank you.